Time is one of the most familiar experiences in human life, yet one of the least understood in physics and neuroscience. Every moment you experience feels continuous, flowing from past to present to future. However, this sense of flow is not necessarily a property of the external world. It is, at least in part, a construction of the human brain. In physics, time is treated as a dimension, similar in structure to space. Events are described as occurring within spacetime, where past, present, and future are all part of a single mathematical framework. In this view, time does not flow in the way human experience suggests. Instead, all moments may exist simultaneously as different coordinates within a larger structure. What we perceive as the passage of time is closely tied to change. Without change, there is no internal reference for time. The brain relies on continuous comparisons between memory and present sensory input to construct the feeling that time is moving forward. In this sense, time is deeply connected to memory and perception, rather than being a standalone external force. Neuroscience shows that the brain does not contain a single clock for time. Instead, time perception emerges from distributed processes across multiple brain regions. The cerebellum, basal ganglia, and prefrontal cortex all contribute in different ways to time prediction and sequence processing. These systems work together to help the brain estimate duration, order events, and anticipate what will happen next. Interestingly, the perception of time can change depending on mental state. During moments of stress or danger, time often feels like it slows down. This is not because time itself changes, but because the brain increases the density of information processing. More detail is recorded in memory during intense moments, which can create the illusion of extended time when recalled later. In contrast, during routine or repetitive experiences, time often feels like it passes quickly. When fewer new memories are formed, the brain compresses the experience, making long periods feel shorter in hindsight. On a biological level, time perception is also influenced by neural oscillations, rhythmic patterns of activity in the brain. These oscillations help synchronize communication between different regions, allowing the brain to organize information into coherent sequences. Without these rhythms, perception would become fragmented and disordered. At a deeper level, human consciousness does not experience time as a continuous stream in real time. Instead, the brain constructs perception in discrete moments, integrating sensory information over short intervals before presenting it as a unified experience. What feels like now is actually a slightly delayed reconstruction of recent input. This means that the present moment is not a precise point, but a short window of time assembled by the brain. Within this window, the brain organizes sounds, images, and sensations into a coherent scene that feels immediate. Physics and neuroscience together suggest that time is not as simple as it feels. In physics, it may be a dimension without flow. In the brain, it may be a constructed experience shaped by memory, prediction, and neural processing. This difference between physical time and perceived time creates a gap between reality and experience. The universe may operate without a preferred now, while human consciousness insists on living inside one. Human memory plays a central role in how time is experienced. Without memory, there would be no sense of continuity between moments. Each perception would exist in isolation, with no connection to what came before or what might come after. In such a state, the concept of time would lose its meaning entirely. Memory does not function like a perfect recording device. It is reconstructive. When the brain recalls an event, it does not retrieve an exact copy of the past. Instead, it rebuilds the experience using stored fragments of sensory information, emotional context, and conceptual understanding. This reconstruction is influenced by the present state of the brain, which means that memories can subtly change over time. Because of this, the past is not fixed in the way we often assume. It is continuously reshaped by new experiences and interpretation. Each time a memory is accessed, it is rewritten with slight variation. Over long periods, these small changes accumulate, altering how past events are understood. The feeling of a continuous present moment is also an illusion created by the brain. Neuroscience suggests that perception operates with a slight delay. The brain integrates incoming sensory information over short intervals, typically around a fraction of a second, before presenting it as a unified experience. This means that what is experienced as now is actually a constructed summary of recent events. Despite this delay, consciousness feels immediate. This is because the brain prioritizes coherence over accuracy in real-time perception. It is more important for survival that experiences feel continuous than that they are temporally precise. The distinction between past, present, and future is therefore not as rigid as it appears. The past exists as memory, the future as prediction, and the present as an active construction that bridges the two. The brain is constantly simulating what is about to happen based on past patterns, while updating these predictions with incoming data. Prediction is one of the most fundamental functions of the brain. Every moment, the nervous system generates expectations about the next moment. When reality matches prediction, perception feels smooth and stable. When there is a mismatch, attention increases, and the brain updates its internal model of the world. This predictive mechanism also shapes emotional experience. Anticipation, fear, and curiosity are all linked to how the brain processes uncertainty about future events. In this way, time is not only perceived, but emotionally interpreted. Dreams provide another perspective on time perception. During sleep, the brain continues to generate internal experiences, but without external sensory input. In dreams, time can behave irregularly. Long sequences of events may unfold in a very short period of physical time, or moments may feel stretched and unstable. This suggests that the structure of time in conscious experience depends heavily on external sensory constraints. Even in waking life, subjective time is flexible. When attention is fully engaged in a task, awareness of time diminishes. Conversely, when attention is directed toward time itself, such as waiting or anticipating, time becomes more noticeable and often feels slower. This indicates that time perception is closely tied to attention, rather than being an independent sensory system. At a deeper level, the sense of a flow of time may arise from the continuous updating of neural states. Each moment of consciousness is slightly different from the previous one, and this gradual change creates the impression of movement. The brain stitches these states together into a narrative, producing the feeling of a moving present. However, this narrative is not an external truth. It is an internal model, constructed for coherence and survival. The universe itself does not appear to require a privileged present moment. Instead, it may simply consist of events related across spacetime, with no intrinsic direction. From this perspective, the human experience of time is both precise and limited. It is precise in the sense that it allows navigation, prediction, and adaptation. It is limited in the sense that it does not fully reflect the underlying structure described by physics. Still, this limitation is not a flaw. It is a feature of cognition. Without it, experience would likely be fragmented and unusable for biological life. The sense of continuity in human experience depends on how the brain organizes information over different time scales, rather than processing everything in a single, unified moment. The nervous system operates through layers of timing mechanisms, each responsible for integrating information across different durations. At the smallest scale, neural activity occurs in milliseconds. Neurons communicate through electrical impulses, and these impulses form patterns that encode basic sensory features such as light, sound, and touch. Without this rapid signaling, perception would not be possible at all. Above this level, the brain integrates information over slightly longer windows, combining multiple sensory inputs into coherent objects and events. This integration process is essential for recognizing movement, speech, and spatial relationships. Without it, the world would appear fragmented, as if each sensation existed independently. Even higher levels of processing extend across seconds. This is where experience begins to feel like a continuous stream. The brain links sequences of events together, allowing actions and consequences to be understood as part of a connected flow. This is also the range in which working memory operates, holding information briefly so it can be used in real time. Beyond seconds, memory systems begin to dominate. Events are stored not as raw data, but as compressed representation. These representations are later reconstructed when recalled, creating the subjective feeling of past experiences. Over time, these stored patterns form a narrative structure, giving life a sense of continuity across days, months, and years. What is important here is that these timescales do not operate independently. They interact continuously. Faster processes provide the raw data, while slower processes provide context and meaning. Together, they create a layered model of reality that feels unified. Even though it is constructed from many separate temporal systems, the experience of now emerges at the intersection of these layers. It is not a single point in time, but a short interval where incoming sensory data and recent memory overlap. Within this interval, the brain stabilizes perception long enough to allow meaningful interaction with the environment. Because this window is continuously updated, it creates the impression of motion through time. Each update replaces the previous one, but the transition is smooth enough that it is not consciously detected. This creates a seamless experience of present. However, this seamlessness is not absolute. Under certain conditions, such as high attention or emotional intensity, the boundaries of this processing window become more noticeable. Time may feel expanded or slowed because more information is being processed within the same physical duration. In contrast, during low attention states, fewer details are encoded and the brain compresses experience more aggressively. This results in the feeling that time has passed quickly. The underlying physical time remains unchanged, but the density of processed information varies significantly. This relationship between information density and perceived time suggests that subjective time is not measured by a constant internal clock, but by the amount of change the brain registers within a given interval. More change leads to a longer subjective experience. Less change leads to a shorter one. From a physical perspective, time does not require an observer to exist. It is embedded in the structure of spacetime and continues independently of perception. However, the human experience of time is entirely dependent on observation. Without a perceiving system, there would be no distinction between past and future. From an experiential standpoint, this separation between physical time and psychological time is fundamental. Physics describes a continuous framework of events, while the brain constructs a selective interpretation of those events. The two are consistent in structure, but different in experience. Continuity, then, is not something that exists inherently in consciousness. It is assembled moment by moment from discrete processes, each contributing a small part to the overall experience. The feeling of an unbroken flow is the result of this constant reconstruction. One of the most fundamental questions about time is why it appears to move in a single direction. In everyday experience, time seems to flow from the past toward the future. Events are remembered after they happen, never before. Causes always precede effects. This directional quality is so consistent that it feels like an inherent property of reality. In physics, however, most fundamental equations do not prefer a direction of time. At microscopic levels, the laws governing particle interactions are largely symmetrical. In theory, many physical processes could run forward or backward in time without violating the underlying mathematics. Yet the world we experience is clearly not symmetrical in this way. The explanation for this asymmetry is closely related to entropy. Entropy is a measure of disorder, or the number of possible microscopic configurations within a system. In simple terms, systems tend to evolve from states of lower entropy to higher entropy over time. This tendency is not because disorder is preferred, but because disordered states are statistically far more likely. When a system is highly ordered, there are fewer possible ways for it to exist. When it is disordered, there are vastly more possible configurations. As a result, the natural evolution of complex systems tends toward increasing entropy simply because there are more ways for that state to occur. This statistical tendency creates what is known as the arrow of time. It is not a force or a law imposed from outside, but an emergent property of probability, applied across large numbers of particles. On a microscopic level, individual interactions may be reversible, but on a macroscopic scale, the collective behavior produces a clear direction. The human experience of time is deeply connected to this asymmetry. Memory formation, for example, depends on physical processes that increase entropy. When the brain encodes an experience, it stores information by creating physical changes in neural structures. These changes are irreversible in practice, meaning the act of remembering is tied to the direction in which entropy increases. This is why memory always refers to the past and never to the future. The brain can only record states after they occur because recording itself is a thermodynamic process that depends on irreversible change. As a result, the structure of memory aligns naturally with the arrow of time defined by physics. Prediction, on the other hand, operates in the opposite direction. The brain continuously constructs models of future states based on past pattern. These predictions are not memories of the future, but simulations generated by current neural activity. The asymmetry between memory and prediction reinforces the subjective sense that time moves forward. At a deeper level, the distinction between past and future may be less absolute than it appears. In the mathematical description of spacetime, all events exist within a single framework. The separation into past, present, and future depends on how information is accessed and processed, not on a fundamental division in reality itself. However, the brain does not experience this full structure directly. It exists within it, processing information sequentially. Because neural processes are themselves thermodynamic and irreversible, consciousness is bound to a directional flow of experience. This means that the arrow of time is not only a property of the external universe, but also a property of biological systems that observe it. The structure of memory, perception, and computation all depend on irreversible change. Without this, experience as it is known would not be possible. Even the feeling of continuity relies on this asymmetry. Each moment of awareness is built upon a slightly different physical state of the brain. These states cannot be revisited in their exact form, which ensures that experience always moves forward rather than looping or reversing. Yet on a conceptual level, time remains more flexible. In theoretical physics, equations can often be rewritten in ways that treat past and future symmetrically. This suggests that the directionality we experience is not a property of the fundamental laws alone, but of the conditions under which those laws operate at large scales. The universe, then, does not appear to flow time in a single direction by necessity. Instead, the direction emerges from the interaction between physical laws, statistical behavior, and the structure of information processing systems like the brain. In this sense, the arrow of time is both objective and experiential. It is objective in that it arises from measurable physical processes, such as entropy increase. It is experiential in that it becomes meaningful only through systems capable of memory and prediction. Without such systems, time would still exist as a structure of events, but there would be no distinction between remembering and anticipating, no sense of direction, no feeling of movement. In everyday experience, it feels natural to assume that there is a single shared present moment across the universe, a universal now, in which everything is happening simultaneously. However, modern physics suggests that this idea does not hold under closer examination. According to the theory of relativity, time is not an absolute background against which events occur. Instead, time is part of a four-dimensional structure where space and time are interwoven. In this structure, different observers can disagree on the timing of events, depending on their relative motion and position in gravitational fields. One of the most important consequences of this is that simultaneity is not universal. Two events that appear to happen at the same time for one observer may occur at different times for another observer, moving at a different speed or located in a different gravitational environment. There is no single, privileged frame of reference that defines an absolute present. This means that the idea of a shared now across the entire universe is not supported by physical theory. Instead, Each observer carries their own local version of time, shaped by their state of motion and surrounding. Time becomes something personal in a physical sense, not just in perception. Time dilation is one of the most direct expressions of this principle. When an object moves at high speed relative to another observer, time for that object passes more slowly when measured from the observer's frame of reference. Similarly, in strong gravitational field, time also slows down relative to regions with weaker gravity. These effects are not merely theoretical. They have been confirmed through precise experiments using atomic clocks placed at different altitudes and velocities. Even small differences in gravitational strength, such as between sea level and higher elevations, produce measurable differences in the passage of time. This reveals that time is not uniform across space. Instead, it is influenced by mass, energy, and motion. The structure of spacetime is dynamic, responding to the distribution of matter and energy within it. In regions near extremely massive objects, such as neutron stars or black holes, time can slow dramatically compared to distant regions. From this perspective, the universe does not contain a single global clock. It contains many local clocks, each running at slightly different rates depending on their conditions. The idea of a universal present moment dissolves into a network of overlapping, but not identical timelines. The human brain, however, does not perceive this complexity directly. It constructs a simplified version of time that feels consistent and unified. This simplification is necessary for functioning in everyday life. Without it, experience would be fragmented across incompatible temporal frameworks. Even though physical time is relative, subjective time feels absolute. This is because the brain uses internal biological processes as a reference system. Neural activity, metabolic cycles, and sensory integration provide a stable internal rhythm that anchors perception. This biological timing system creates the illusion of a consistent flow of time, even when external time is not uniform. Another important implication of relativity is that the ordering of distant events can depend on the observer. In some cases, two events separated by large distances may not have a clearly defined sequence that is agreed upon by all observers. Instead, their order can shift depending on the reference frame used. This challenges the intuitive idea that the universe unfolds in a single, fixed sequence of events. Instead, the sequence itself is part of the observer's perspective. Reality, at its deepest level, is not arranged as a single timeline, but as a structure where multiple valid descriptions coexist. Despite this complexity, local experience remains consistent. On human scales, differences in time caused by relativity are extremely small. They do not disrupt everyday perception or biological processes. As a result, the brain operates as if time were uniform, even though physics shows that it is not. This gap between physical reality and perceived reality is a recurring theme in the study of time. The universe operates according to precise mathematical rules that allow for variation in time, depending on context, while consciousness constructs a stable narrative that hides this variation. In this sense, the experience of time is a simplified interface. It is not a direct representation of the underlying structure, but a usable approximation that allows organisms to function within it. The simplicity of this interface is what makes coherent experience possible. Without it, each moment would be split across countless, slightly different temporal conditions, making stable perception difficult. Instead, the brain integrates these differences into a single stream, producing the familiar feeling of continuous time. At the most fundamental level, time remains one of the most difficult concepts to define in absolute terms. Physics describes time as part of the structure of spacetime, where events are arranged in a geometric relationship rather than a flowing substance. Yet human experience describes time as something that moves, something that passes. This difference suggests that time may not be a single unified thing. Instead, it may exist in different forms, depending on the level of description. At the physical level, time is a coordinate within a mathematical framework. At the biological level, time is a process tied to change, memory, and energy consumption. At the psychological level, time becomes an experience constructed by consciousness. Consciousness does not observe time directly. It observes changes in states: light entering the eyes, sounds reaching the ears, internal signals within the body. From these changes, the brain builds a model of continuity. That model is what is experienced as time. Without consciousness, the concept of time as felt passage would not exist. The universe would still evolve according to physical laws, but there would be no internal perspective from which that evolution is experienced as movement. Time, in this sense, becomes inseparable from the existence of an observer. This leads to a subtle but important distinction. Physical time describes relationships between events. Experiential time describes how those relationships are interpreted by a system capable of awareness. One is structural, the other is interpretive. The relationship between the two is not fully understood. However, it is clear that the brain does not passively receive time. It actively constructs it. Neural processes integrate signals over short intervals, compare them with stored memory, and generate predictions about what comes next. The result is a continuous narrative that feels unified and stable. This narrative is not fixed. It is constantly updated. Each new moment slightly rewrites the internal model of reality. The feeling of now is the point at which this updating process is currently occurring. It is not a location in time, but a process of integration. In this way, the present moment is always moving, because the system defining it is always changing. The brain does not step through time like a traveler, moving through a landscape. It continuously rebuilds the landscape from within. Some interpretations of physics suggest that all moments in time may exist equally within a larger structure, often described as a block universe. In such a view, past, present, and future are equally real, and the flow of time is not a fundamental feature of reality. Instead, it is a feature of how information is accessed within that structure. If this interpretation is considered, then the sensation of moving through time becomes an emergent property of consciousness, rather than a fundamental property of the universe. It arises because information is processed sequentially, and because memory preserves only certain states of that sequence. Even if time is fully described by static relationships in spacetime, experience still unfolds in a directional way. This is because consciousness is embedded within physical systems that operate through causality and thermodynamic irreversibility. Each moment of awareness depends on physical changes that cannot be reversed in practice. From this perspective, time is both real and constructed. It is real as a structure that organizes events and governs interaction. It is constructed as an experience generated by systems that exist within that structure. There is no contradiction in this duality. Instead, it reflects two different levels of description of the same underlying reality. Physics describes what exists. Consciousness describes how part of what exists is experienced from within. When viewed together, time becomes less like a flowing river and more like a vast relational structure. Within that structure, observers trace paths that feel continuous, because their internal processes are designed to integrate change into coherent sequences. The feeling of time passing is therefore not an illusion in the sense of being false. It is an accurate reflection of how information is processed by a system embedded in a changing universe. However, it is not a direct reflection of the universe as a whole. As the brain rests and external input fades, this constructed sense of time can soften. Thoughts slow, boundaries between moments become less distinct, and the intensity of temporal structure can decrease. Yet even in rest, the underlying mechanisms continue to operate quietly, maintaining the minimal framework needed for awareness. In this way, time is not something separate from existence. It is a description of change, a framework for relating events, and a pattern that emerges wherever information is processed sequentially. And within that pattern, consciousness experiences a continuous present stable enough to navigate reality, flexible enough to adapt, and subtle enough to dissolve into silence when attention fades.